Okay, let's look at today's lecture. So I want to take a look at linear regression, and we'll take a look at just kind of talk about the ideas behind it. But you guys are already familiar with linear regression because you've taken Stats 101A. But we'll take a look at how do you approach even just fitting a simple model like linear regression using tidy models. So we'll start, first things first, we'll load up the tidyverse called library tidyverse, and then library tidy models, and this will load up kind of all of the different packages. These are basically collections of packages, and these will get loaded up here. Okay, so yeah, before we get into that, let's just do a quick review of linear regression from Chapter 3 in Introduction to Statistical Learning with R. And this just kind of sets forth some basic principles. And so we'll take a look at simple linear regression, and then we'll expand that to multiple linear regression. So we will work through an example, and this is the advertising data example. I believe this is a generated data set, but the idea here is the outcome variable that we're looking at is sales. Sales as in measured in hundreds or measured in thousands of dollars, and we are trying to predict, what forms of advertising have different effects on the sales. And so we have three predictor variables. We can spend money on TV advertising, money spent on radio advertising, and money spent on newspaper advertising. So this is clearly an older data set, an older example. Lots of advertising today is spent on online advertising or, on YouTube streaming sites, all kinds of things like that. But we'll imagine this is maybe 30 years ago or something, before online advertising was really a major player. So TV, radio, and newspaper. And so, just the initial explorations, we can kind of plot sales against each of these variables individually. And so we can see in general, as TV spending goes up, sales goes up. As spending on radio advertising goes up, sales goes up. As spending on newspaper goes up, also sales goes up. Although the strongest relationship seems to be with TV, radio seems to be next strongest, and newspaper seems to have the weakest of these relationships, but it does appear that there is still some kind of positive trend, but we do see quite a bit of scatter in the newspaper relationship between newspaper and sales there. But we have a bunch of questions that we might want to answer, right? One is there a relationship between the advertising budget and sales? And if so, how strong is that relationship between advertising budget and sales? And this applies for each of the different forms of advertising. Which media, which form of the advertising contributes, to sales? How accurately can we estimate the effect of each medium, whether it's TV, radio, or newspaper, on the sales? How accurately can we predict future sales if we know the values coming in? Is that relationship even linear? And finally, is there an interaction between the advertising media? Is there like a synergy, kind of like you get something more than just the sum of the individual parts? These are all kinds of questions that we might want to explore. So in simple linear regression, it's simple because we just have one predictor variable related to the output, and I think this is something we're already very familiar with, but you write something like B0 plus beta 1, or beta 0 plus beta 1 times x is plus epsilon is going to be what our random variable y is. We assume epsilon is a random variable that's normally distributed with mean 0, and then the fitted values, our predictions y hat, is going to be our estimated intercept, beta 0 hat, our estimated slope, beta 1 hat, times whatever our input value is for x. Okay, and And the way we estimate what beta 0 hat and beta 1 hat should be is we pick the intercept and the slope that minimizes the residual sum of squares, right? So we say, the residual is the difference between what the actual value y sub I is and the predicted value y hat sub I. Okay, so for each individual we have the actual value, and then we also have the predicted value, and we want to know, hey, what's the difference between the actual and the predicted? And that difference, okay, is our epsilon for that individual data point. Y hat is really found just by doing beta hat 0 plus, or beta 0 hat plus beta 1 hat xi, so we can also kind of plug that in there. And therefore the total residual sum of squares is going to be the sum of all of the different epsilon terms, e1 squared, e2 squared, all the way up to e sub n squared. And we can expand this out, and we get the RSS to be, basically each of these things, all squared up. Okay, and simple linear regression is already a solved problem, but this is kind of the idea here, right? So here, if we're going to say, hey, we want to predict sales based on the TV advertising budget, this is kind of what our scatter plot looks like. Our fitted line is this blue line, and then the vertical distance between each dot and the line is our residual. Okay, so this being a linear model, we can only make a prediction for any one given x value. So if x is, say, equal to, I don't know, whatever this is, 140, okay, we can see there's several values where x is equal to 140, and we can only make one prediction for any of these things, right? Here's when spending was 200,000. We have several observations when spending was 200,000. We have one prediction, which is where the blue line is there, but we're going to have a whole bunch of different residuals, and we're going to try to minimize the total of all of the squared residuals. Okay, and we can use calculus to figure out the coefficients that will minimize RSS. I think this is covered in, actually Stats 100C, and these are the solutions, right? So beta hat 1 is equal to this, the estimated slope is equal to that, and once you have the estimated slope, then your estimated intercept is going to be basically y bar minus beta 1 hat times x bar, and this will give you the coefficients, the intercept and the slope that will minimize the residual sum of squares. So this is a solved problem. We know what intercept and slope we need to pick. Okay. Another way we can think about this is we can think about this as having kind of two knobs, two coefficients that we have to estimate. And the minimum RSS is achieved when beta 0 is equal to 7.03 and when beta 1 is equal to 0.0475. This plot over here represents kind of the contours of the values of the RSS for when we have slightly different beta 0 and beta 1 values. So the minimum is achieved at this location with the red dot. If you overestimate beta 0 a little bit, you're going to end up getting slightly more RSS, okay? And the farther you get away, like if beta 0 is too big, then your RSS gets much bigger. If your beta 0 is too small, it gets much bigger. If your slope is too steep, your RSS goes up. If your slope is too shallow, your RSS goes up. So this is kind of what we see. So the minimum is down here, but as we have different kind of circles indicating higher levels of RSS. So going up to 2.2 to 2.3 to 2.5 to 3 or something like that. Okay, so if we plotted this in 3D, you get a paraboloid. It's a little bit difficult to see with just the way this thing is shaped, but it's kind of like this elliptical bowl, kind of a paraboloid that you have. Okay, let me also show this this web page. Okay, And so this illustrates another kind of, we can visualize how this works. So in this data set we have 7 data points, and I have 2 knobs here. This knob, this first knob, changes the intercept. So if I turn the knob to the left, the line slides down. When I turn the knob to the right, the line slides up. Okay. This knob controls the slope, so I can turn it and the slope becomes shallow. I can turn it and the slope becomes steep. What these represent the RSS, the residual sum of squares. So as with this current line, the vertical distance between each dot and the red line, which is our prediction line, is our residual. And you can see we've drawn a square out of it, okay? And that square, I guess, appears over here as well. So here, blue and orange and green and red and purple and brown and pink each kind of have a square. So, one thing I can choose is I can choose to slide the line. So this red line is very close to the purple and pink dots, also pretty close to orange and green, okay? And so the residual for orange and green is pretty small. Residual for purple is pretty much non-existent. Residual for orange is also very small. And we can see that when we square them, we get these very small squares. However, the line is far from the blue, red, and brown dots, and so those residuals are big, and their squares are also very big. I could try to slide the line down, and when I slide the line down, now the residuals for blue, red, and brown, very, very small, because the line goes through these dots very closely. So very small blue residual, very small red residual, very small brown residual. However, the residuals for green and orange and purple and pink are much, much bigger, and so the total RSS is quite big. So, we want to try to find a happy medium where overall, and it's kind of tough, the overall RSS is as small as possible. So what do we want? Something around here. So looking at this, so I don't know what the true answer is, but these are the kinds of things. And so you can see, if your slope is too big, you get big RSS. If your slope is too small, you get big RSS. And as you kind of get to the center, you're going to find some kind of happy medium somewhere around here. Same thing with the slope. If your slope is too small, you get really big RSS. If it's too big, you get really big RSS. And you get something like that. You often see kind of an inverse relationship where if the slope gets, if the intercept gets bigger, then you can kind of make your RSS smaller by decreasing the slope, or you can kind of slide the line down. If your intercept is small, you can shrink your RSS by kind of increasing the slope. So something around there. These are some of the ideas there. Okay, so that's just kind of a little interactive feature you can check out that gives you a sense of like, okay, yeah, as we increase the intercept, we're going to get kind of different values, and you can get the sense of, it gets bigger or smaller until you get somewhere close to the middle, and then the same with the slope. It gets bigger or smaller until you get the intercept. And you also see a little bit of this inverse relationship that if the intercept is too big, then the slope, to kind of keep the same amount of total RSS, the slope shrinks or the opposite. Okay, but how do we assess the accuracy of our coefficient estimates? How do we know whether our intercept and our slope is even is any good? Because the data that we have, we understand that this is a random sample, and that if we had collected the data on another day, we'd probably get different numbers. Well, not probably, but almost certainly we would get different observations. And then if we fit simple linear regression to those observations, okay, we would get slightly different slope and intercept values. Okay, so the coefficients that we have right now, our slope and our intercept, is just one possible set of estimates out of many possible ones. So we can kind of get a sense of how accurate our coefficient estimates are by just asking this question: what if we drew another random data set from the population and then we estimated the slope and intercept? How different would that slope and intercept be from our current slope and intercept? So to do this, we got to kind of simulate the data, right? So we're gonna say, hey, we know what the population looks like, we know what the true slope and what the true intercept looks like, but let's just kind of play around with the idea of different random data sets. Okay, so here is, on the left, is a plot of simulated data. Okay, the true line that has the relationship between x and y is given by the red line. Okay, we generate some random data, okay, around the red line. So that's the true line, but because of random noise, sometimes you get a big outlier up here, or a big outlier down here, or something like this and that. And so we say, hey, fit these dots, and what is the slope that you get? Slope and intercept you get. So you get a slightly different, so this is the estimated line. It's this blue line. And so we can see the slope on the blue line is a little bit steeper than the true red line, and the intercept is a tiny bit lower than the true red line. So looking at the 0, it's a tiny bit lower than what the true red line is. Okay, so that's what we have on the left here. On the right is, well, what if we did the same thing again, but we did different random dots? Okay, so if we did different random dots and we fit a line, we get one of these light blue lines. And we did this a whole bunch of times, and each of these light blue lines represents different random dots, and we fit a simple linear regression line. Okay, and so we see, yeah, you know what? All of these different lines that we fit, they're all slightly different from each other. Some are shallow, some are steeper, some are a little, but overall, we're kind of getting the red line, getting close to the red line. Sure, this one's a little bit too high. This one has an intercept that's a little too low. This one has a slope that's a little too low. This one has a slope that's a little too high. But overall, I would say these light blue lines do a fairly decent job of estimating the red line. Okay, so that's where we are. So for any one given random sample of data, we can't expect our least squares regression line to be exactly perfect. We're not gonna, if I just pick one of these light blue lines at random, it's not gonna be line up with the red line perfectly, and we can't expect that because that estimated light blue line is subject to the random noise that appears in our data. Okay, but the idea is if we kind of followed this process a whole bunch of times, generating a whole bunch of different random data sets, fitting a least squares regression line, then in the long run, if we averaged all of these different light blue lines, overall, that the average of those things, like if you averaged all of the intercepts, averaged all of the slopes, it would equal the red line, okay, in the long run. Okay, and that's what it means when we say the least squares regression line is unbiased. In the long run, the process of fitting a least squares regression line is eventually going to get the true relationship in the population correct. It'll get the true slope, it'll get the true intercept. But that's assuming you get infinite data. Okay, but again, when you have a random set of data, it's not going to be perfect. But overall, in the long run, we can expect it to be unbiased. But yeah, so that's the issue. Okay, of course, we don't know if the one sample that we do have actually gives a very good estimate or not. Okay, so we recognize that our estimates of beta 0 and beta 1 are based on the random sample that we have and the error that we have in that. Okay, and so if we get another random sample of data, it will produce slightly different estimates of beta 0 and beta 1. And if we did a whole bunch of these things, we could basically get a sampling distribution. A whole bunch of different beta 0 estimates, a whole bunch of different beta 1 estimates, and we can say, all right, what is the standard deviation of this sampling distribution, or what is the standard error of these coefficient estimates? Okay, and these are the formulas for the standard error of the slope and the standard error for the intercept. Okay, and so you can see the amount of error in the population, that epsilon error. Remember the random noise that's generated around the true relationship, that sigma plays a role in the standard error. Basically, as you get more variance in the generated data, your standard error is going to be bigger. Okay. The other thing we also see is that the sample size plays a role. As our sample size increases, the denominator is also going to get bigger, right? The denominator is going to get bigger, and so as you have more and more sample size, these standard errors will also shrink. So I guess the other things, some assumptions, we have to assume that the errors are uncorrelated with the variance. Okay, but when you look at these graphs, okay, back here, we can see the variance growing. We can see the variance growing. So that that kind of assumption is violated. So I wrote, this is not true in the diagram for the relationship between sales and TV, as we can see that errors tend to increase as the budget at TV budget increases. Okay, but that said, we can still kind of continue our analysis, because overall it still gives a pretty good approximation. Okay, so one thing, also another thing that you might notice is that the standard errors of the slope will actually be smaller if the xi's are more spread out, right? So if the xi's are more spread out, that is xi minus x bar, if you have a big difference between xi and x bar, you're going to get more spread out things. This will produce a larger denominator, and your standard error for the slope gets smaller. And this kind of makes sense, because if the region where x is observed, okay, is really tight, okay, then if you got one point right here and one point right here, the fitted slope can vary quite a bit. So like if you have just some error here, just making small changes to where my finger is, right? I'm just going up or down a tiny bit, you can see the slope changing quite a bit, okay? Whereas over here, if the observations of x are more spread out, and I just kind of want to wiggle x, if I have x go up or down a little bit, the amount of slope doesn't change as much, okay? Whereas if the points are all really close together, if I just wiggle my finger a little bit, make my right finger a little bit higher than my left finger, the slope goes like this. If I make my right finger a little bit lower than my left finger, the slope is suddenly steep down. Okay, over here they are flat. If I make my right finger a little bit higher than my left finger, it goes just ever so slightly up. If I make my right finger a little bit lower than my left finger, it goes ever so slightly down. So the amount to the variance, the standard error on the slope is affected also by basically how spread out your x values are, right? So if your x values are more spread out, we can be more confident in our estimate of the slope here. Okay, now that we have a standard error for the estimates of beta 0 and beta 1, we can create confidence intervals and perform hypothesis tests to see if the parameters that we get are significantly different from 0. Okay, 95% confidence intervals are roughly basically beta hat plus or minus 2 standard errors, or beta 0 plus or minus 2 standard errors. If the resulting confidence interval contains 0, then that basically means 0 is a plausible value for the slope, okay? And our data does not provide evidence that the slope is significantly different from 0. Or, in other words, if the confidence interval contains 0, then maybe the relationship between x and y is doesn't actually exist. That the slope term for x and y could actually be 0, and therefore x doesn't really influence y. That's a possibility. We can also perform a hypothesis test. So if you want to talk about the slope, you can do beta 1 is equal to 0. That's the null hypothesis, meaning there's no relationship between x and y. We're saying the slope between x and y is 0. Versus beta 1 is not equal to 0, that there is a relationship between x and y. Now, you can also make it a directional hypothesis test by using a greater than sign or using a less than sign. But these are kind of your basic hypotheses. And then you would have a test statistic t, and we calculate this with by doing beta hat 1 or beta 1 hat minus 0 divided by our standard error. We look that up in the t-table with n minus 2 degrees of freedom. If we end up getting a large t, meaning our coefficient is much larger than the standard error, then we would say, yeah, we have evidence that there is a relationship between x and y. We have evidence that our slope is not 0. Okay. On the other hand, if your test statistic ends up being small, beta 1 hat is not that much bigger than the standard error, okay, then you don't reject the null hypothesis and you say, yeah, we don't have evidence that the slope is significantly different from 0. This is how you would go about creating a linear model using kind of the LM function in base R, right? So you read in your CSV file, advertising.csv, okay, is the file there, and we will get rid of basically the first column, which is I think the row numbers, okay, and we're going to say I want to predict sales based on TV, okay, sales based on TV. That's going to be our model. We ask for the summary of the model. Our intercept is 7.0. The standard error is 0.45. So our test statistic is 15.36. 7 is 15 times bigger than our standard error. So that's very significant. Okay. Our slope is 0.047. So not very huge, but the standard error is really, really small at 0.00269. So our test statistic, 0.047 divided by 0.00269 gives me 17.67. Also a really big number. Rule of thumb being, t over 2. If you have lots of degrees of freedom, is going to be significant. If you have only a handful of degrees of freedom, then you need a bigger t. But here we are at 17, 17 times the standard error. So that results in a p-value that's practically 0. Okay. Let's revisit this, but now I want to introduce using tidy models, okay? And I've got it here in the notes, but let's also, I want to kind of run it simultaneously in R as well. So let me try to get everything to fit here. So let me read this in here. Okay. Oh, cannot find. Let's see. Set working directory to source files location. All right, will this work now? There we go. Okay. So, okay, so here's the advertising data set. We have TV, radio, newspaper, and sales. And here we fit just regular old LM, our linear model, to it. This is what we get so far. We have the same results as seen. Okay, let's load up tidyverse and tidy models, or maybe I already done this. Okay, so first I'm going to run this line, tidy models prefer. Okay, tidy models prefer just tells R if you have a conflict with the names of different functions, because sometimes tidy models offers functions that have the same name as other functions in other packages, where you're going to say we want to use the tidy models version. Okay, all right. What I'm going to do is using tidy models, and within tidy models there's the package parsnip, is I want to create a linear regression model. Okay, and so let me just show you the help for linear regression. So within parsnip, this is going to, so this is in parsnip, we want to create a linear regression model. And when we fit a linear regression model, we have a few options. Okay, as far as we have, I guess, engines, and we have engine specific pages. And so you can use the regular old base LM engine. But there are additional things. Well, there's GLM, which you might have seen as well, but then you can also fit Brule, which basically uses I think PyTorch or some kind of neural network there. GLMNet is a little bit more of a flexible thing that allows you to implement, say, lasso or ridge regression for shrinkage and stuff. And then there's, you can also use Keras for neural networks that will basically try to estimate these parameters in slightly different forms. Okay, but here we're going to just kind of stick with the base one, and so we start a linear regression model, okay, with parsnip, and then we run this command set engine to LM, and that will set the engine of the linear regression to the base LM, and we're going to store this as an object called LM_model. Okay, so now I have LM model, and if I ask what LM model is, it says, hey, this is a linear regression model specification. Okay, we actually haven't fit it to any kind of data. All right, so all we've done is we've created a model specification object. Currently has no values, nothing kind of going on inside of it just yet. And so in tidy models, so you first specify what your model looks like, and then you fit the model to the data. Okay, so here we take that LM model object and we pipe it into the function fit. Okay, so I take the model specification, pipe it into the function fit, and within that function fit we provide the formula, that is, we want to predict sales based on TV, and we specify that the data comes from the advertising data frame. Okay, and then that is going to form the LM formula fit object is what we're going to call it. Okay, so I'm going to create LM formula fit, and into that I'm going to store the results of piping the linear model specification into the function fit, where I say I want to predict sales based on TV, and the data is advertising. Let me just make sure this matches sales, TV data, advertising fit. Yep, LM model. Okay, so I do that, and now I have LM form fit. Let's see what the output of LM form fit is. Okay, so now we have a parsnip model object. Basically, it has called the LM function with formula sales as TV, data as our data, and these are estimated coefficients. Same as basically what we got when we fit the LM model using LM, way back here in one of these earlier things that we did. Okay, so that's what we have there, right? There's an alternative way to fit the data. Okay, so here we used the formula, and we said predict sales based on TV. You can also use XY fit. So XY fit would be a little bit, if you're familiar with Python's nomenclature and the Python syntax for, say, using scikit-learn, you don't use a formula and do sales predicted by TV. You have basically a vector for sales and then an X matrix. Okay, so here we're going to run fit XY. We'll take our model specification object, our parsnip model specification. So again, this thing is still the same model specification from parsnip, but we're going to say, hey, this time I want to fit it, do an XY, and I will provide you what the X is. And so the X is from advertising. We're going to select the column TV, and then from advertising, we're going to select the column sales. So this is basically using the dplyr notation from the tidyverse. We're just basically selecting this column and this column. And that's going to form my LM another fit. So I'm going to call this LM XY fit. And into this, we are going to take our LM model, and we're going to do fit XY. And into the X, what we want is advertising, select TV. And then we want to do Y is equal to advertising, select sales. Okay. So let's go ahead and take a look at what LMXY fit looks like. And it says parsnip model object, and we get the same results as we would expect. Same results, same intercept, same coefficient. Here looks a little bit funny. We have dot dot y tilde dot, but basically this is the result of parsnip translating the instructions we provided, which is we gave our objects in kind of matrix form and said, hey, fit the model. Okay, if you want to take a closer look at the results, you can do it within parsnip. You can also kind of look at the original kind of model specification. So if you want to kind of get back the way it would look if we called LM ourself, which I think is, when I call, this is kind of the output of, when we just do LM. You can extract this out, okay? So I can take LM formula fit, and then what I can do is I can say extract model, what's it called? Extract fit engine, sorry. Extract fit engine. And this will pull out basically the exact same, this is what LM would produce if you called LM directly. Okay, so right now it seems a little bit funny because we are familiar with LM, and so it feels like, why are we bothering using parsnip? The idea here is parsnip gives us a unified way to specify models. Okay, so we're familiar with LM, so we know how to specify models with LM, and it's pretty simple and straightforward. But there are other packages out there like GLMnet and Random Forest and Ranger, which also produces Random Forest. And there's a whole bunch of other packages, and for each of them, the way you specify your model changes a little bit, and it's a little bit annoying having to read the documentation every single time and saying like, okay, how do I reshape my data so I can specify the thing? And it's frustrating. Here with parsnip, you just learn how to specify a model in parsnip, and then you can use these other things by calling set engine. So you say set engine LM, and parsnip will translate the instructions into basically the necessary call to use LM. you can say set engine random forest, and it will translate the instructions into the command that the random forest package would use. You can say set engine glmnet, and it will translate the instructions into the way glmnet would want it. And so here we start off with LM because we're familiar with it, but we can see that, yeah, you know what? When I use parsnip and I specify the model, it's able to produce the LM call that's necessary for us. Okay, and if you want to kind of extract out the original call or the original fit engine, as if you had called it directly yourself, you have that. Okay, and if you want to say get summary from it, you can do that, right? So you can do LM form fit extract fit engine, and so this is basically as if we called the LM directly, and then if we called the LM directly, then one of the things you might want to do is you might want to ask summary on the results, and this is the summary table for those results. Okay, and this is what we saw earlier, with the t values and the p values. It's all there. It's all there, and parsnip translates this for us, so our life is much easier. Okay, we traditionally would not go through this process of using parsnip and then extracting the original model and things like that, because parsnip creates a unified framework for specifying the models, and then it also, so not only it specifies the models so that the engine can run it, but once it runs it, it also takes the output of the engine and it kind of formats it in a unified framework. So you kind of get the same kind of information out from each of these things as well. So when you do LM, you can get the information from summary, but then if you called random forest, or if you called glmnet, or any of these other things, the results it returns a little bit different. Okay, so to use the tidy models thing is you can kind of just take the thing that you fit. So here we have LM formula fit. So this is the result of using parsnip, and we've got the estimates. What we can do is we can extract out all of the information by calling tidy on it. Okay, when we call tidy on it, it returns back this tibble with the coefficient estimates, the standard error, the t statistic, and the p-value. Compare this to what we had earlier. And so it's the exact same numbers: 7.03, 0.0475, standard error 0.45, 78. It rounds off a little bit. 0.0269, test statistic 15.4, 17.7, and our p-values, it gives us more precision here. Okay, so all of this information is here. One thing about this though is now that it's in tidy form, okay. I'm going to call this coef. I can, it's a tibble. I can extract out. Let's say I want to get the estimate. I can say, row 1, column 2. Okay, and then I can, whoops. I think I can pull this to get that exact value out. If I want the p-value, I can say, hey, I want this thing row 1, what is that, column 5? Okay, and I can pull that value out, and I get these terms. So rather than just, because in the summary table here, there's not a quick way to get this. There's not a quick way to get this, right? So so this is the LM model here. I can, where is it? Structure model. I think it's under not model DB, model. Okay, I think it's under coefficients, residuals. How do I get the standard errors? I don't know. So for model, I can get coefficients. I have that. So if I do summary model, so on LM, how do I get the standard error? Structure model, is it somewhere? Is it stored in there? Yeah, I don't, maybe I'm missing it. But actually, I don't know how to get the standard error out of when you have the LM model. If I wanted to get this value, I'm not quite sure how to get it. Okay, but with you know, LM, when you call tidy on a parsnip fit, you know, you get back the exact. It's in a data frame, so you know you can filter, or you know you can just slice to row 1, and you can select, you know, the 4th column, and then you can pull that. Okay, and you can get out these values exactly. Okay, so that's one of the nice things, is you can call tidy, right? And then all of the other same thing with all of these things. So when you call summary on the original LM model, you have a bunch of other stuff like the multiple R squared, adjusted R squared, and all of those things. Okay, you can get you know, you can get all of these things by calling glance. Okay, so instead of formula fit, you can call glance, and again, it produces it into a table. All right, and so this multiple R squared being 0.6119, okay, you can get that out, right, from the table glance, right? So from glance, you can just say select, I want the first thing, and then you can pull it, and you get your R squared value, or your adjusted R squared. You know, you want it from the 2nd column. Okay, adjusted R squared will be, you know, 0.6099, right? So that adjusted R squared right there, also right here. Okay, but if you know, if you wanted to do something with this directly from the summary table, I think it's not as easy to do with LM. With LM, you know, all of this information is there, but it's not as easy to kind of just get these values out to kind of start working with them. And it's all done when you use parsnip. So that's a really nice feature. Okay. So yeah, so here you go. If you wanted to do it, if you want the R squared value, you can call glance, select, you give it the name R dot squared, or you know, select 1 because it's the first column, and then you call pull, and then so pull. So whenever you do select, it always gives it back in the form of a tibble. And so if you want to extract the actual, you know, vector of values there, or in this case the single value, you call pull, and it, you know, gets rid of the tibble data structure, and you have that number there. Okay, if you want to make predictions, you can just take your fitted model and throw it into predict. Okay, so here I want to say, all right, I want to make predictions for when TV has the value 200, TV has the value 150, and TV has the value 100. So we're going to create test cases here, and that's what this line is going to do. We're going to create a table of test cases. So test TV is this data frame with just these 3 values, 200, 150, and 100. And then I can call, take our model, LM formula fit. This is the result of calling parsnip. We're going to call predict, and we say our new data is going to be found in this data frame, test TV. So new data is equal to test TV, and then it says here your predictions. Your predictions are 16.5, 14.2, and 11.8. Okay. If you want, you can predict it on the entire kind of advertising data set, right? So in advertising, we have 200 rows, and you can take LM formula fit and predict new data is equal to advertising, and you'll get all of the predictions there. Okay, and it produces 200 predictions because we have 200 observations. Okay. If you want, you can also not just get the prediction, but you can also create, like, say, a prediction interval. So when you call predict on the advertising, you can specify type. Type is equal to prediction interval. Okay, and you get a prediction lower and a prediction upper. I think you can also do a confidence interval, and you get a upper and lower bound for the confidence interval. So here, prediction lower, prediction upper, prediction. I wonder why it says that. But this is the confidence interval. So the confidence interval is kind of the range of where you think the mean is, the average. You're 95% confident that the average of the is going to be somewhere in between here and here, and then the prediction interval takes into account the random error that exists, in the data generating process. And we're saying, I'm confident that the next observation is going to be somewhere between here and here, which is a much wider range, right? So much wider range for the prediction interval because it takes into account the random variation. The confidence interval is kind of the prediction, the interval for where the mean is. So so here, if you want, you can kind of bind all of these things together. Let me so here I said take advertising, select just the column sales and TV, and then bind additional columns. So we're going to say, hey, run predictions, LM formula fit advertising. That's going to give me this column dot predictions, and we're going to bind that to the results there. And then on top of that, we will bind the prediction interval for the lower and the upper. So we're saying, if TV is 230.1, my prediction is 17.97, and then I'm 95% confident that a random value generated around here is going to be between here and here. And sure enough, 22.1 is within the bounds of our prediction interval, and it seems like most of these values, again, the way we set up our prediction interval, we expect around 95% of them to be within the bounds of our prediction intervals. Okay, so we have that. All right, so again, I just kind of want to pause and say, in the beginning, using tidy models does feel cumbersome, right? Because we're already kind of familiar with LM, we're probably used to it, and so having to do all of this stuff with tidy models and specifying the model and then quote fitting the model and then getting these results feels a little cumbersome. However, once you get accustomed to using tidy models, it's going to be really easy for you to pick up a new package that has an entirely new way of specifying the models and using that thing. It's going to be really easy to kind of interface with those different systems out there. Okay. Otherwise, you're going to be spending a ton of time reading the documentation of that package, which, granted, isn't a terrible thing, but if you're just trying to fit the models, okay, of these different things kind of quickly, one after the other, tidy models is really going to speed things up for you. Okay, let's see. All right, so the residual standard error, it's roughly the typical amount that the response will deviate from the true regression line. All right, so these are just kind of ways for us to kind of measure how accurate our predictions are. Okay, so that residual standard error, you kind of take basically almost like the average of the RSS, and then you take the square root of that, right? So you're dividing RSS not by n minus 2, kind of taking into account some correction factors there. Okay, your R squared value is basically 1 minus the RSS divided by the TSS. So how much is explained by the model is your R squared value. The part that's unexplained is your RSS, right? So the part that's unexplained is RSS divided by TSS. That's like the percentage of your of the sum of squares that's unexplained, and R squared is will be then how much that is explained, right? So TSS being the total sum of squares, RSS being the residual sum of squares. For simple linear regression, R squared ends up being your correlation coefficient R, literally squared. It works out that way. Okay, so let's say we have this very simple data set, okay, where my x values are 1, 2, 3, and 4, and my y values are 2, 6, 4, and 8. The correlation between x and y is 0.8, and when you fit a fitted line, the intercept is 1 and the slope is 1.6. Okay, correlation 0.8. If I do LM, y predicted by x, intercept is 1, slope coefficient is 1.6. And this is kind of what the plot looks like. Here's my point 1, 2, 2, 6, 3, 4, 4, 8. And this is the prediction line with an intercept of 1 and a slope of 1.6. And so we can see when x equals 1, my prediction is 2.6. When x equals 2, my prediction is 4.2. When x equals 3, my prediction is 5.8. And when x equals 4, my prediction is 7.4. Okay? This blue line represents the mean of the y's. It's 5. Okay? The green lines are the difference between each dot from y bar. Okay? And so when you take the difference between the dot and y bar, that's going to be your contribution to the total sum of squares. Okay? So TSS is basically each dot from the average y, in this case 5. So we can say, we're basically saying, hey, how different is each dot from the mean? So, you get this one, y is 2, the prediction is, the average is 5, so that's 3 squared. This is y is 6, the average is 5, that's 1 squared. Y is 4, the average is 5, 1 squared. The, y is 8, the average is 5, 3 squared. So total sum squared is 20. That's going to be the sum of the green lines squared. Okay, your residual sum of squares is the difference between what we predicted and what the actual value was. So over here we predicted 2.6, the actual value was 2, so it's 0.6 squared, 0.36. Over here, the actual value is 6, we predicted 4.2, so that's going to be 1.8 squared, gives me 3.24. 1.8 squared for this one is the red line, orange line squared, 3.24, and then this orange line squared, 0.6 squared gives me 0.36. When you add them up, you get your RSS of 7.2. 7.2. And so your R squared value is basically the total sum of squares minus the RSS. So 20 minus 7.2, that gives me, 12.8. 12.8 divided by total sum of squares of 20. 12.8 divided by 20 gives me 0.64. 0.64 is my R squared value, and no surprise, that is correlation 0.8 quantity squared, which is always going to be the case when we're doing linear regression. Okay, so that's simple linear regression. Let's now talk about multiple linear regression. All right, so in multiple linear regression, we're able to create models that have more than one predictor variable. So you'll have, an x1 predictor, an x2 predictor, up to xp. Okay, and it's linear because you just kind of multiply each of these things with some kind of constant, beta 1, beta 2, whatever, and then you add them up. Okay, and again, epsilon term normally distributed with mean 0. And then so when you make the predictions, you're going to have your estimated coefficients, beta 0 hat, beta 1 hat, so on and so forth, multiplied by each of your x values and to get your y hat. Again, when we do this, we try to minimize the RSS between our each individual value y sub I and our prediction y hat being the sum of all of our estimated coefficients and multiplied by the x terms. And that's going to be the RSS there, and we try to do that. And again, this is kind of a solved problem. So here I have x1 and x2 And when you fit a linear regression model, if you have two predictor variables, linear regression model is going to form a plane between x1 and x2. Okay, and we choose basically the angle of this plane to minimize the sum of the squared residuals, which are illustrated here as the vertical lines between each dot and the plane. So let's try this again. Now with the advertising data. Okay, we have three predictors. We have dollars spent on TV, dollars spent on radio, dollars spent on newspaper ads, and our responsive sales. So again, we're going to just start off simple linear regression with each variable one at a time. Okay, so using tidy models, this is kind of how it's going to look, right? I'm going to say we're going to specify a linear model using Parsnip. So this is a model specification, just saying I want to do a linear regression model. The engine we're going to use is LM. And then I'm going to create different fitted models. Okay, this one is going to be a model fit between TV and sales. Okay, and so I'm going to do LM model. I'm going to call fit. I'm going to say predict sales based on TV from the advertising data. I'm going to create another thing where I fit the same model, but this time just change the variables. Okay, so I don't have to do an entirely new call. This is going to be the radio fit, predict sales based on radio. Okay, and then again, just for illustration, if I wanted to use the other specification form fit XY, which sometimes you might need to do if your data already comes kind of separated, where X is in its own matrix and Y is its own matrix or vector, you can also specify it this way. We didn't have to. I could have just done sales tilde advertising. I'm sorry, sales tilde newspaper, data equals advertising, and that would have worked. But this will be our newspaper fit. Let me go ahead and run that same code chunk down here. Let me just go ahead and run all of these things. Okay, predict there. We'll create that. Sorry. So I'm going to go ahead and run all of these things. So now I have a bunch of these fits. I've got the news fit, the radio fit, and the TV fit. Okay, and then I can call tidy to kind of take a look at each of these things. I can see, all right, what is the statistic and the p-value for each of these things. So the test statistic for TV is 17.7, the test statistic for radio is 9.9, the test statistic for newspaper is 3.3, the kind of the smallest, but they're all still significant. TV is significant on the order of 10 to the minus 42, radio is significant on the order of 10 to the minus 19, but newspaper is still significant on the order of 10 to the minus 3. So when we model simple linear regression for each of these variables, each variable does have a coefficient that is statistically significant. Okay, so I can just kind of throw this into tidy. Again, if you wanted to, you could extract the model fit and then call it into summary so you get something a little bit more familiar like the LM summary. But using tidy, you get basically the same information, and it's in a tibble, which I think is nice to read. Okay. Here I'm going to create a combined fit where we're going to put in all three predictors: TV, radio, and newspaper. So I'm just taking, again, the same linear model specification, but this time I'm fitting it with a different formula: sales, TV plus radio plus newspaper. This is going to be my combined fit. So I guess, if you think about 101A, this would be kind of like, I guess, backwards stepwise variable selection. Well, first we just did one at a time, but here to kind of pick, we're going to just throw all of the variables in. There's only 3, and we throw them in here. Okay, and so now when we do this, what do we notice? We notice that newspaper is no longer significant. It's a little bit hard to read, but this is 8.6 times 10 to the minus 1. So 0.86. The p-value is 0.86. You can see the test statistic. It's pretty close to 0. Negative 0.117. So not that big of a deal. The estimate for the coefficient is 0.001, and the negative 0.001, and the standard error is 0.00587. So our coefficient for newspaper in this combined model is not significant, and so that might throw us off a little bit, right? So when we looked at newspaper by itself, it was significant. In the combined model, it is not significant. What's going on here? Okay. So I'm just taking some text straight from the textbook here, okay? But we can, if we look at all of these variables and we say, let's create a correlation matrix, okay? What's the correlation between TV and radio, and TV and newspaper, and sales and stuff? What we see is that, some of these coefficients aren't super highly correlated, but there is positive correlation between newspaper and radio, okay? So the correlation between radio and newspaper is 0.35. This is not huge, but it's also not nothing. And that means that in the market where the media market where there is higher radio advertising, there's also higher newspaper advertising, okay? And so, let's suppose that the multiple regression is correct. Newspaper is not associated with sales, but radio advertising is associated with sales. So in the market where we spend more on our radio, okay, we also tend to spend more on the newspaper. And if radio is correlated to sales, we're going to see the positive relationship between radio and sales, but those are also happen to be the markets where we're spending more on newspaper. And so therefore, even if you just look at newspaper and the relationship to sales, it's going to appear that that there's positive correlation there, even if newspaper advertising is not directly associated with sales. So that's something that could happen. Okay, so this is kind of you learn about multicollinearity and issues like that, and so that certain variables, when you look at them one at a time, appear to be correlated, but when you look at them all together, they are not. Okay, so let's so that's that. Okay, let me introduce a little bit on a workflow. Okay. So again, please do your reading. So look up Tidy Modeling with R and read the textbook here. Okay. And so a lot of this stuff we came from fitting models with Parsnip, and you can see how they also set different engines, GLMNet and Stan. And there's even a function called translate that lets you see what is the exact kind of call that's going to be used for each of these different things, okay? And you can kind of see how it works. And here they've done it for the Ames training data, and we've been working through the advertising data. But what we want to do is we want to kind of establish a workflow, all right? So with a workflow, right now, we're just going to create a workflow, and then we're going to add the model to the workflow, okay? So yeah, I said earlier, when fitting simple linear regression models, we specified 3 similar but different models. An alternative to specifying different models and fitting each of them is to use a model workflow. So I start off by specifying my model. This is my linear model specification, but I'm also going to create a linear model workflow. So I start off with an empty workflow. This is just workflow, and then we add the model LM model. Okay. And then here I have a list of all of the different formulas I want to try to fit with my workflow. Okay, so I want to do sales predicted by TV, sales predicted by radio, sales predicted by newspaper. I'm going to try doing sales predicted by TV, radio, and newspaper, sales predicted by TV and radio, sales predicted by TV and newspaper, and sales predicted by radio and newspaper. And I think this is all of the different combinations we could possibly have. Okay, so I could have repeated the process and done it for each of these things, but I can also just kind of specify them all in a single list, right? And so we have this workflow, and we're going to fit all of the models and evaluate the predictive performance on all of these things, okay? So here I create something called a workflow set, okay? A workflow set. Now there's a lot of kind of terms here. Don't worry too much about it right now, okay? But here in Tidy Models, I create a workflow set, and my preprocessor, so workflows, you have a preprocessor, you have a model, and then you fit each of these things. So here we're going to say I want to basically fit the model for each of these different formulas that I have. Okay. Right now I just have one model, and that's the LM model. If I wanted to, I could specify more than one model here, and it will kind of cross-match every single one. So if I had two models here, if I had a LM model and let's say a GLMNet model or something like that, okay, then it would list off 14 workflow sets. Okay, it would have LM for the TV formula, and then GLMNet for the TV formula, LM for the radio formula, and GLMNet for the radio formula, and so on and so forth. We would have 14 of these things. But right now I'm just going to try. I just want to try the 7 different models formulas out on the LM model. Now you can see all of these things. This table is a little bit tough to read. We have the workflow ID. This is basically just the name of the workflow, and you can see what it's done is it's taken the name from the formula and the name for the model. So it's just done TV LM, and then the formula here was radio, and it does radio LM, and the formula here was news, called news, and then we have news LM, and so on and so forth. So again, if I had GLMNet, I would also have TV underscore GLMNet, radio underscore GLMNet, news underscore GLMNet, but I don't. Okay. And so these are the IDs, or the way it's named the things. And then we have the info, and the info itself is a tibble, and we can extract out that tibble if we wanted to. There's options right now, it's empty. These are all zeros. And then the results right now is empty because we haven't actually fit any of these things. So if you wanted to take a closer look, I can say, hey, let's look at the first thing right here. Okay. And it's going to have information about the workflow, which has the preprocessor and the model. The preprocessor is basically the formula, or later on we'll learn about recipes. But right now it's just the formula, and then we have the model, which is linear regression. And again, if you had something else, it would have more information about that. And then within the workflow, we have the workflow, and so if I wanted to, I can extract out the workflow itself. The workflow itself has information about the workflow, and we can see, okay, the preprocessor is this formula. It's a formula preprocessor. What is that formula? Sales as predicted by TV. What's the model? The model is a linear regression model with the detail that the computational engine is LM. So all of the information as far as specifying the model is all in this table as far as advertising underscore models goes. Okay, and then let's say we want to try fitting all of these models and then evaluate how well each of these models performs. Okay, because this is kind of when you do machine learning, you don't really use the summary tables as much. Okay, they play a role. And certainly when you're using something like LM, you care about the p-values and the statistics and the standard errors. But a lot of kind of future machine learning models, or the other machine learning models that we're going to be using, don't really have these traditional assumptions about, normally distributed errors and things like that. And so you can't really create test statistics. And so how do you evaluate performance? How do you compare, how well the random forest is working compared to the linear model? Because with the linear model, you can get, sure, p-values, but the random forest isn't really going to give you p-values in the same way that the linear model is going to. So what it comes down to is we say, well, how well does this model predict? How well does this model predict? Okay, and the way we evaluate prediction performance is with cross-validation, right? We say, all right, fit the model to this data and predict this subset. Fit the model to this data and predict this subset. And so we can fit the linear model to the data and have it predict on the remaining part. And we say, okay, this is how close you got. And then we try the other model. Make prediction, fit it to here and make predictions on here. How close did you get? And so to facilitate that, we'll use Tidy Models v-fold cross-validation. So here I'm going to say, hey, take our advertising data and then just do tenfold v-fold cross-validation, tenfold cross-validation. Okay. Now, in this thing, I did not do the initial split between training and testing and whatever. We're just taking the entire thing and doing v-fold cross-validation. Again, best practice would be you have a big data set, you do an initial split between training and test, and I showed you how to do that in one of the earlier lectures. And then once you have your training data, then you do v-fold cross-validation. You split that up into more folds. I'm going to just for illustration here, we're just going to take the advertising data set. It's not even that big of a data set. I only have 200 data points. I'm going to do tenfold cross-validation, so I'm going to get 10 sets of 20. We're going to fit our data to 180 points, or fit our model to 180 points, have it predict on the remaining 20. But we do this 10 times for each model. Okay, so you can see if you didn't have an automated tool, it's going to get really painful to do something like that, right? Because then you'd have to fit this TV linear model 10 different times, making predictions 10 different times to measure the errors. And then you do it again for radio. And so you end up fitting the model 70 times, 7 different models, 10 times each, to make predictions to kind of evaluate the performance. But, oh, thank goodness, Tidy Models automates this whole procedure for us. So I set up the folds using v-fold cross-validation here. And now I'm going to run workflow map. We're going to map the fitting of the model to all of our kind of resamples, okay? So after I've taken the advertising data and I've done tenfold cross-validation, I have my folded advertising data, which I've called add folds, okay? And so this is, if you think back to my earlier lecture on cross-validation, the way it works is when you have the fold, okay, it automatically has the split, okay? Here, if we looked at it, it would be like 180-20, all right? This is the repeated folds here. But you get, each of these splits here, it would be like 180-20 for a total of 200, okay? And so we do that. We're going to fit the resamples, all of the different advertising models, okay? All of the different advertising models are right here. We got 7 different models, 7 different LM models, 7 different formulas. We're going to fit them, okay, onto the advertising folds. We're going to fit those resamples, and we will store all of those results back, okay? So this is going to try all of these things. It's going to fit 10 times each model, each of the 7 models 10 times. It's going to do 70 of these things kind of rapidly in succession. So I guess I'll go ahead and I'll run it for us. Okay, so let me news fit. Yeah, so we can extract out each of these things. This is our combined fit. Okay, so I'm going to set up my workflow. Here's my formula list. here are all of the advertising models that we've got. Each of these things. We'll set up the v-fold cross-validation. And so now I'm going to run this. Okay, so it's going to basically fit the thing 70 times. So it takes a few seconds to do it. It's done. Okay, I guess as soon as I said that, it wraps it up. So here with advertising models, what I want to do now, okay, so if I ask, so remember advertising models when we first ran it, everything in results was empty. If I take a look at advertising models now that I've fit them all, okay, now we have stuff under results, okay? Under results, we do have stuff. So I can do advertising models, results, oops. Let's see, advertising models. Do I want the first one? That's our first column. Oh, it's a result. Okay. So we have a whole bunch of these things. Okay. So under we have the results of tenfold cross-validation. So we can see, I think there's going to be 7 of these things. Okay. So when I say, hey, results, when I expand on this, we get the tenfold cross-validation here. And it did it for all 7 of them. Okay, so for each of them, we can see the individual tenfold cross-validation. So if I do say, let's just look at the first one. This is the tenfold cross-validation for the very first model that got fit, the TVLM. And then from there, you can extract out, say, the metrics. Okay, dot metrics. Gotta put that in quotes. All right, and then so for each of the 10 things, we get out the RMSE for this first split, 180 to the 20. We can get the RMSE for the next 180-20 split. We get a different RMSE, 3.21, 3.57, 2.9, and so we can see the different kind of results for each of these different things. If you wanted to take a look at that, right? And you can go through, so that was it for the TV model. We can go to the results and we can go to the second one, which was not TV, but I think radio. And so you can see the RMSE is a little bit higher for all of these things. You don't have to go through this. There is just this function that says collect the metrics. So you don't have to go through every single one manually. So we can do advertising models, and we call collect metrics. Okay, and so this collects it for us. And our metrics, there were 2 of them, RMSE and R squared. It gets it all of them, and it gives us the mean for each one. And we can just filter to dot metric is equal to RMSE. All right, and so this is what we have. And so we can kind of compare the RMSE for all of the different models. So for TV alone, the mean RMSE, okay, so remember when we looked at advertising models and we looked at the results, we could look at the TV results, and we had, the 10 different cross-validation fits, and we take the average, we get 3.25. When you use radio, you get average of 4.28. With newspaper, you get average of 5.11. When you take all 3, combined all, your RMSE is 1.67. If you just do TV and radio only, your RMSE actually goes down to 1.66. Okay, TV and newspaper gives me 3.1. Radio and newspaper gives me 4.32. So the best fitting model regarding RMSE is going to be the one that uses only TV and radio as a predictor there. Okay, so that's the result that we get for that. So that's pretty great. Okay, I don't know if you guys are excited. I'm excited. I think Tidy Models is so cool because, again, the idea of having to do tenfold cross-validation manually, like if you told me I had to do this myself, I would cry, because you gotta split your data, into 10 different subsets, fit it to 180, fit it, and then make predictions for the remaining 10, record all of those things, measure your errors, and then I got to repeat that 10 times again just for the TV model, and then I got to do it again for the radio model. And so I end up having to fit it 70 different models on this thing. Oh my gosh, it would be so painful. But again, you saw it with the workflow map. We fit all of the different models very quickly. It collects all of those metrics, and we can compare them. That's amazing. Okay, anyway. So we would say the one with the best performance, is, there's a typo, it should say 1.65 is the TV and radio model. All right, so suggests that the variable newspaper actually doesn't improve the predictive performance when we're trying to make predictions for novel data. Okay, that is that. That's kind of our introduction to tidy models. Please do read your homework or read the textbook and start playing around a little bit with tidy models, and follow the examples there. Okay, we'll wrap things up here, and we'll see you later.